This breakout session focuses on the transition from tube type to solid state transmitters for TV and radio stations. We're pleased to be joined by Stephen Rossiter from Gates Air, our conference presenting sponsor. Stephen is the Senior TV Applications Engineer for Television Transmission Group at Gates Air in Quincy and Mason, Ohio. He's worked in the broadcast industry for more than 25 years, starting in the U.S. Army as a microwave systems and telecommunications technician and engineer. Stephen joined Harris Broadcast Division in 1998 and has also worked at Dielectric Communications. He works with the ATSC committee and is a member of SBE. Stephen?
Good morning, everybody. One thing about presentations, when I do presentations, I don't follow the rule about give the presentation, then ask questions. Guys, if you have a question, let's get it out there up front. You're all most of the guys in here are engineers, and some of them very accomplished engineers, because I don't know all the answers, but most of you guys, between everybody, does know the answer. So if there's a question and you can answer it, right, and I can't, please speak up, okay? So I like it to keep it interactive. So getting underway, the first question that comes up is always been efficiency. I go out there and I go and look at transmitters and and the first thing everyone says is, well, I want a solid state transmitter because I want it to be more efficient. Well, let me tell you, efficiency is not always a good reason to change from a tube to solid state. So first thing we're going to talk about is considerations, tube or solid state balanced amplifiers, and then we're going to talk about packaging. And we'll kind of show you what I mean here. So if we start looking at tubes, the original IoTs, right, those big tubes that you guys have out there in the field, they were about 32% efficient. They really weren't that bad. That's the tube itself. Now, when you throw all the other stuff in, the cooling and fans and all the other things that are, incorporated in that dropped that efficiency to about 28% efficient for a standard IoT. But when you look at other newer IoTs, an example, multi-stage depressed collector, right? You could get very high efficiencies out of those. Up to, especially with energy saving IoTs, you can get up to, 60 to 70% for the tube itself. That means you're going to be, with all the extra stuff, somewhere in the 40 to 50%. So when you look at that, and then you go back and you start looking at solid state devices, and you go, okay, well, the solid state devices, if I look at a class AB amplifier, for example, right? What was the best efficiency would I get for a TV UHF channel, right? Would be 19%, 18% for a class AB amplifier. Well, that being said, why would I change from a tube to a class AB solid state amplifier if the efficiency of the tube's so much better? So if we look at progression over time, the best efficiencies overall, when you start looking at UHF television, is like that 20%, 19%, give or take. Now, FM was a different story. FM, you could get much higher efficiencies out of a solid state amplifier, okay? So you could get, 60% out of that. Well, you can get the same efficiency out of a tube. So you have to question yourself, what changed? Why is the industry going from a tube to solid state? Because if it's efficiency is the only reason, it's not a very good reason, you think about it. So when you look at solid state devices, especially the newer LDMOS devices, okay? The newer LDMOS devices, the reason why we've really gone to them is because of packaging. The innovation of how that device, that solid state device, was packaged. So when we start looking at the packaging advancements in that technology, ruggedized LDMOS devices, which are new to the industry, and then we go back and we look at the tubes. Tubes were a single point of failure. if you had a tube fail, you were off air. Unless you were one of those lucky guys that had 2 tubes, right? Or a backup tube, then you could get back up on air. But, you know, most broadcasters had 1 tube, okay? So if they lost it, they were off air until they got something to replace it with. Solid state devices, if you put multiple LDMOS devices in parallel, right? Now I have many devices, and I can do the same power level with the same footprint or less footprint than a single tube. You also have to think about the RF system that goes behind that. Okay, tubes being a single amplifier, right? They put off, I'll call it emissions, out-of-band emissions, and those out-of-band emissions would hit the filters, whether it be typically a reflective filter. If it hits the front end of a reflective filter, what do those out-of-band emissions do? They came back to the amplifier, and they caused the amplifier or the tube not to work correctly, okay? So to resolve that, what'd they do? They made CIF filters, great big filters with hybrids on the front end of them, okay? And those hybrids was what sent part of that emissions over to a load. So that's the reason why, if you look at the old tube transmitters, why the RF systems were so humongous. They were big. They were big because a single tube had to have a CIF filter. So that was one other reason. Now, tubes, they take up a lot of space. I've got the high voltage portions of them. I've got the space of the tube. I've got the cooling of the tube. All of that took up a lot of space. And that didn't include the control cabinet that needed to control all that, okay? So when we start looking at tubes compared to solid state, it's really, a lot of it has to do with footprint, the size. And the size was determined by the packaging, the new innovation of how to package solid state devices. So the other thing about tubes that I always point out is tubes are high voltage devices. So 36,000 volts, give or take, okay? And if you look at that and you compare that to a solid state device, which is 50 volts, right? Which one would you consider safer? Which one's easier to maintain? So even if the efficiency is better with a tube, when you think about the new innovations in packaging, and you think about the reduced footprint, and you think about all these other piece parts, that's what makes solid state so much better than tubes. Now, that doesn't necessarily mean that tubes are gone. Tubes can still be out there and will still be out there as we go through in the future. One of the other innovations was the Daughtry amplifier. Well, guess what? I always say it's an innovation. It's an innovation because of new technology and how it's implemented, but the technology isn't new. As you can see, it was actually done in 1936. So it's an old technology, been out there for years, but because of packaging, how the LDMOSs are packaged, right, we can now use that technology that we couldn't use in the past. And this is what a Daughtry amplifier looks like. It's actually 2 amplifiers. We have one, which is what they call a carrier average amplifier that does the average power. And then we have a peak amplifier, or the peaking amplifier, and that is a second amplifier just to amplify all those peaks. So the combination of the two helps give you that efficiency that we're looking for. So, and how it's packaged. So that's a little bit about why I would go with a solid state transmitter instead of a tube type transmitter. It really has to do with how it's packaged. The efficiency is not necessarily the reason. Now, if you have an old IO2, like the old Sigma transmitters that you saw the picture of earlier, makes sense, because if I look at that UHF transmitter, I can get 28, 29% if I really tweaked it really good, you know, where in a solid state LDMOS today, using a 50 volt LDMOS, I can get efficiencies of 38 to 42%, depending on the size of the transmitter. The bigger the transmitter, actually the more efficient it is. So whether it's liquid or air also determines what that efficiency will be. So that would be the biggest reason why I would go with that. And it's the same thing for the FM as well. Packaging has changed a lot with FM devices, with those LDMOS devices as well. The efficiency has gone up. We have devices today that the individual device is 85% efficient. So if you think about that, and there's a good example of exactly that sitting on the table over there at the Gates Air booth. There's a 1 kilowatt transmitter that's only 2 RU. So that just says, how big was your old 1 kilowatt transmitters years ago? Quite large. So it all has to do with how it's packaged and how the technology is used today. So I'm going to move on to air or liquid cooling, because a lot of customers like air, because that's what they've always used in the past. And the original solid state transmitters, which were Class AB devices, right, were typically air-cooled transmitters, but they still took up a lot of space. So let's look at, if I look at an air-cooled transmitter of today, what are they? They work well with existing infrastructures, because a lot of times you already have that air cooling or the HVAC cooling there. It reduces reliance on outside space. I've got a transmitter inside the room. I don't have to have space outside, so I don't have to have ice covering. I don't have to have any of that outside. Also, it's outside of the elements. It's inside a controlled environment. Simplified operations. We don't have no pumps, no heat exchangers, no liquid leaks. Those are the advantages of air-cooled. Maintenance, well, you got to clean filters, okay? It doesn't matter if it's inside or outside, there's still going to be filter cleaning, okay? So there is a small amount of maintenance involved, but I don't have to worry about maintaining liquid lines. I don't have to worry about maintaining a heat exchanger outside. So those are some things that I can think, well, that's an advantage. And typically, in colder environments, especially if you look at places that are in the mountains and things like that, those are actually using the heat, the excess heat from the transmitter to help heat the building, right? And it works quite well, because you just turn the air conditioner down and turn the heat down. The transmitter does the job. So those are some advantages of air-cooled. So component architecture, you have the transmitter power supplies, okay? We'd like to use an off-the-shelf hot swappable power supply. And the reason is because they're very efficient, about 96% efficient. We look at air cooling, air distribution. So exciter switching units and dual exciters, all of that is kind of incorporated into this as well. So air cooling, typically the transmitters of today, air cooling is from the front through each one of the amplifiers and then out the back. Then you have a choice of what to do with that air, okay? So air-cooled modules, you can see that there's an air-cooled module there. And then redundant fans. Whenever you do an air-cooled, you really want to have the redundant fans, because fans are a moving part. They're always going. We use variable speed fans, but you always want a redundant one, so that if something happens to that fan, you have time to take it off and put another one on. And you don't want to have to do it with the you want to be able to do it with the transmitter running. So you want to be able to hot swap that fan out. Well, the new designs on transmitters are designed exactly that way, especially for the air-cooled. So what are some ways or methods of looking at air cooling? I can grab air from outside, right? Bring it in right into the transmitter, right? Through the transmitter, and then I can blow that air back outside again. So now I reduce my heat load to my room. I don't have to have as much HVAC, right? Everybody sounds like a great idea? Well, it is, but there's always that catch. The catch is energy costs typically would be low. Installation costs are high, because now I got all this extra ductwork, okay? And I've seen this a lot, especially with the old platinum transmitters. You guys are familiar with those, where they put all this fancy ductwork on them, and you know what? They spent most of their time cleaning filters. they were always at the site cleaning the filters. The air coming into to that transmitter, all those filters had to be cleaned all the time. Okay? Maintenance, so maintenance costs get high because you got to have an engineer out there to change filters. Okay? Now, site visits, that means it's going to be pretty frequent. Those filters have to be changed or have to be cleaned. Okay? Humidity control. Electronic devices, as you know, right? You got to control the humidity. You don't want condensating moisture in an amplifier. And those fins will condensate moisture. So how do you control the humidity when you're drawing air from outside? It's great if you're in an environment like the desert where you've got a dry environment, but if I'm in Canada or I'm in Maine, well, guess what? Try to control the humidity there. Or Florida, for example. That's even worse. Now you got a hot, humid environment. Trying to control the humidity in that kind of environment is almost impossible. So there are some drawbacks to trying to pull air from outside through a transmitter and then back out again. Can we do it? Yeah, we can do it. But I always look at the environment. I always look at, do you have the staff to maintain that? Okay? Because a lot of places now, your transmitter room is unattended. No one's there most of the time. So what's the other way? The other way is looking at it from an air cooling method of just air conditioning the room. Well, energy costs get high because now I've got this great big heat source and now I got to keep it cool. So I got to have air conditioning. Okay? Well, that is quite a heat load for a transmitter, especially a transmitter that's 38 to 40% efficient. That means I got roughly 60% of that heat coming out into that room. Okay? So that's one thing to keep in mind. Installation costs are low, unless you count the HVAC guy that's got to come out and put a new HVAC in, or a bigger HVAC. Maintenance costs, well, they're pretty medium. They're not going to be very high, but you still got to maintain that HVAC system that's cooling that room. That's part of that cost. Site visits are fairly infrequent because it's just circulating the air in the room. Your HVAC is doing its job, and it's keeping that room dust-free for the most part. I won't say that every transmitter room is dust-free or even bug-free. So, seen a lot of that. Humidity control is excellent because now I've got that air conditioner taking care of that humidity in that room and getting that humidity and keeping that room dry. And then dust and dirt is excellent because it's a sealed environment. I've got air conditioning going on. So, but now let's look at another method. Another method is pulling outside air into the room and then through the transmitter, using the room as a kind of a buffer, and then out from there, and then drawing that heat out. So energy costs, well, they're the highest. And the reasoning is because I'm drawing warm air from outside, and it's typically normally warm, moist air from outside into the room. Well, my air conditioner then has to work twice as hard because it's trying to dehumidify and cool that warm air coming in. Okay? That's then, that room acts like that buffer. The transmitter is going to be happy. It's seeing the cool air because the air conditioner is doing all the work. But your costs are high. Okay? And I have seen this particular system done a lot, especially in other parts of the world, Africa being one of those places. Okay? The drawback is also they tend to not take care of the filters because you still have to filter all that air that's getting pulled into the room. Okay? So what happens is the filters get dirty, they break down, and now that dust and dirt's inside the room, and it's now being pushed through the transmitter. So that's one of the drawbacks there. Humidity control, I'll call it medium. And the reason it's medium is because that a large volume of air in the room is buffering the humidity, and the air conditioner is taking care of that. So dust and dirt goes back to that dependent on the filters. So that's air cooling. what we'll talk about next is liquid cooling. What are the advantages and disadvantages of liquid cooling? Reduces cooling requirements. When you look at a liquid-cooled transmitter, okay, you're taking heat from that FET, right, and you're putting it into the liquid. Well, the heat transfer between the FET and the liquid is much better than air. So you get better heat transfer. Well, what does that mean for the transmitter? Well, that means that I can drive that FET a little bit harder, okay? I don't want to drive it all the way into saturation, but I want to drive it as close to saturation as I can. Backed off just a little bit because of the high efficiency amplifier types, okay? I don't want to drive it all the way. I want to drive it just a little bit less. And that gives me the best efficiency. Well, if I can get rid of the heat, I can do that. And liquid being a better heat medium or better heat transfer medium, then I can get rid of that heat much easier than I can with an air-cooled. So I can drive it harder. Gives me better efficiency. So, simplified operations, less filters to clean, okay? Filters are really my heat exchanger outside, which I could put a screen on it if I want, or I can put a filtering on it. But basically, that heat exchanger, I go out there with a hose and I can just wash it out. So it helps reduce some maintenance there. Now, the other side of that coin is I have to check to make sure that my cooling lines are free. I got to check to make the heat exchanger doesn't get full of lint and dirt and debris from outside. That's a kind of a downfall. So there are some things that we got to think about. I also have to have ice protection over those heat exchangers because I don't want the ice falling off the tower, damaging my heat exchangers, which in turn I go off air because I lose my liquid, right? So those are some different advantages, disadvantages. One advantage is it's modular. I can do the whole system as a modular design. I can have the multiple heat exchangers and multiple cabinets for my transmitter, okay? And then kind of the old saying that you always hear, you know, you can't mix liquid and electronics, you know, well, it's not necessarily true. So let's look at the architecture just a little bit. So I have the transmitter. Power supplies, a lot of vendors provide liquid-cooled power supplies. And there's nothing wrong with that. The only thing is 90% of the time those power supplies have to be a special design, okay? And they're typically located inside the module itself. Now, the downfall to that is now if I lose a power supply, and that's the most common thing to fail in a transmitter is typically the power supply. The next thing would be the module itself, the PA or the amp, okay? If I lose a power supply, I lose that module, okay? Because I got to pull that module out to get it repaired or replaced, right? So if the module or the power supply is separate from the power amplifier module, I can keep a power supply on a shelf and just pull it off and put it in, right? So there's advantages to having the power supply outside of the PA module, okay? And then typically you'll have one power supply running one amplifier or one PA module. So we've got redundancy because now if I have multiple PA modules, because we're talking about solid state, so I'm going to take all these FETs and put them in parallel, and once I put them in parallel, I can combine them together with hybrid combiners, combine the whole system, and finally an output. The other advantage to that is I'm combining with hybrids all of those FETs, okay? An example, a 1 kilowatt UHF transmitter, okay, would have approximately 30 FETs in there to get to that point, okay? Okay, or less, depending on the use of it. Is it UHF? Is it, you know, FM? But the point being is those are all combined with hybrids. So do I have to have a CIF mass filter when you think about it, the output of that transmitter? Well, no, I don't, because I've got all those hybrids in there. Any out-of-band emissions coming from my amplifiers, those out-of-band emissions will hit each one of those hybrids as they combine everything together, and part of that out-of-band emission gets sent to the load, okay? It gets reflected off the filter, comes back, and it does exactly the same thing. It starts hitting into the loads, okay? All those reject loads that are there. So the advantage to a solid state device is really having all those hybrids as well. Now I don't have to have that great big CIF sitting out there. I can use a much smaller filter and just keep it reflective and use a reflective filter for my mass filter, you know? I would love it if the FCC would ever say, well, you don't need a mass filter. Just go ahead and just let her rip. Well, that'd be great, but that's not practical. And repack can tell you that because you got all these channels now packed into very small bandwidths. So power amplifiers themselves, power supply, power amplifiers, okay? We can put multiple amplifiers in each module, okay? And that being said, we can get more power, okay? Internal, external pump system. When we start talking about liquid, I got two different pump systems I can use. I can use an internal to the cabinet. I can use an external to the cabinet, still indoors, or I can either put that indoor pump module, I can put it outside. So I got multiple options. Downfall to that is putting a pump module outside, it's now subject to the elements, and when you subject moving parts, especially to the elements, guess what? Sooner or later, they're going to fail, okay? Just like a fan on a heat exchanger. Sooner or later, they're going to fail. So, one of the things on the pumps and the fans is we actually use variable speeds. So, when we look at the fans outside, I vary the speed of the fans. We use inverters for doing that. And what we're doing is we're doing nothing more than changing the frequency. So if I have a 208 service at 60 hertz, those fans run at 60 hertz. But I can turn that frequency down to, say, 30 hertz, and then the fans will slow down. Well, if I turn it down to 0 hertz, the fans are going to stop. So if it's, 20 degrees outside, I'm going to run those fans just as slow as I can, because at those temperatures, I want to keep the liquid warm, first of all. I also, does two things. One, it saves energy. Two, liquid cooling, something like that, and if I can maintain the temperature of the liquid, the worst thing on electronics devices is expansion and contraction. And when you heat and cool something, they expand and contract. If I can maintain the heat or the temperature pretty consistent with all the FETs and all the devices in a transmitter, I actually increase the life of that product, okay? So it's important that if I can lower those fan speeds down to 0, and I can maintain the temperature consistent, I don't get that expansion and contraction. So that's an important other piece of this. I can also do variable speed pumps. Now I have to have a minimum speed, okay, because I gotta have minimum flow, okay? But the point is I can raise and lower the speed of the pumps as well. If it gets really hot outside, I speed them up. If it gets cool outside, I can slow them down. The fans react very quickly. The pumps take a little time because they're still controlled by the liquid temperature. So, all right, plumbing flexibility. Not all vendors provide you that flexibility. We at Gates Air, we tell you, if you want solid copper, and soldered, we can do that. If you want press fit copper, which is what we're finding most customers today, makes it easy to install, it's a solid copper, and they know it's robust, okay? We can provide that. Or we can provide hose too, if you want a hose. I will tell you, the hose today is extremely robust as well. It's actually designed for liquid fuels and things like that. So it's very robust hose, but it will still break down over time. That's just the nature of hose. But we can do all of those. It's really an engineer's choice as to what we have. So, same thing with FM. We look at the transmitters. We got power supplies. We mentioned about 96% efficient. Mean time before breakdown. Power amplifiers for the FM as well is liquid cooled. We can do those. And then distribution systems. We also use chiller plates within the transmitter for reject loads. Okay, so that way we can liquid cool all those loads as well. Now, do we use air-cooled loads in a liquid system? Yes. the big reject loads for combining multiple cabinets together, we would use a air-cooled load. But most of the loads inside each individual cabinet would be liquid-cooled because we want as much of the heat into the liquid as we can. Heat exchangers. We can put these in many different locations. We can do a lot with them. As far as mounting is concerned, in other words, we can mount them right to the side of a building. We've mounted them on top of the building. We've actually stacked multiples typically up to 3 high is what I could do. I don't like doing 3, I like doing 2 because it's a little hard to get to the top one. But the point is we've got multiple options for that. Now, what is the downfall of a heat exchanger? I still got to protect that heat exchanger from my tower icing and all that, unless you live in a place that doesn't have icing towers. But I've seen ice in Texas, so it happens. Goes back to the pump systems again, internal, external, okay, all of that's available. One last thing I really want to touch base on that's really important is transmitter control systems. The IoTs had a very extensive control system, but a lot of that has changed now. We've actually taken the FM line and the TV line, taken the control systems or the GUI interface that you see, and really combined them together so they look very similar. And the reasoning is this: as an engineer, I don't know if you're going to have an FM station in that same room as your TV. And if you have the GUI interface that looks very similar between the two, most engineers grasp things very quickly, and they automatically know, oh, well, this is just like my TV transmitter. It has all the data in the same locations. It's easy to find. They get used to it. So the way we've designed our GUI interfaces is designed it so from a management standpoint, we make it easier for the engineer. So meter status commands, SNMP, so we provide them, requires MIBs, so we provide that. And then GUI interface, the health and status, cooling, all of these things, all these different parameters are provided there, and remote enabled. So we can actually do upgrades and things like that as remotely as well. So really, in the end, this last page kind of just goes through the same benefits that we've been talking about overall. And lower the cost of ownership. You look at a liquid-cooled transmitter. The goal is to get the cooling outside, use a high-efficiency amplifier, and reduce your cooling costs. That helps your overall cost of ownership. So that's one of the key factors there. And then less space, less footprint. Remember, we went to a solid-state device, not because of efficiency, but we went to a solid-state device because it's less footprint, okay? It's easier to maintain. I don't have the high voltage. I have lower voltages, and not only is it easier to maintain, but it's safer to maintain. So different parameters for liquid and air cooling. If you look at liquid cooling, and you look at FM with HD, we can do that. All these different parameters we can do. But you're talking about, if you talk about a UHF transmitter or VHF, we can do 1 kilowatt all the way up to 200 kilowatts, if that's what you want to do, in a solid state transmitter by just adding cabinets together. So redundancy becomes a huge thing in solid state where you didn't have that in a tube type transmitter. So same thing with the air cooled. We can put multiple cabinets together, doing that with multiple devices, multiple FETs. We can actually have a much more robust system than the old tube type transmitters. So liquid air is more of a preference. So really the question in the end is, what would you choose as an engineer? What is your preference? All right. Any questions? Go ahead.
I was at the new BNS transmitter. He showed me his new transmitter. It's at the Gates.
Yeah.
Two 10-kilowatt cabinets for the combiner.
Uh-huh.
And I said, well, each of those trays, there's 10 trays in each one, all
because in the liquid-cooled transmitters, the type of connectors that we use, they're actually a connector inside of a connector, so they come together like this, and they're actually opening up two valves at the same time. And the same thing is when they come apart, they're closing those two valves at the exact same time. Now, can they leak? The answer is yes. Anytime that you have a valve, anytime that you have any liquid-to-liquid connection, can you get a leak? The answer is always going to be yes. Can you get a drip out of it? The answer is still yes, okay? Now, the coolant that's used, and this is the part that most guys don't know, the coolant that we use is Prestone, okay? And the reason why we use Prestone is designed for multiple metals, but there's also another additive to Prestone that most people don't realize is there. It's a lubricant. So, while that coolant is going through the system, places like those valves are getting lubricated as well because there's a small amount of lubricant inside that Prestone in the coolant. That's the reason why we say 50-50% coolant, okay? 50% distilled water, 50% the actual Prestone coolant, which you can buy at any AutoZone, okay? The point being is there's multiple reasons for using it. One is getting rid of bacteria inside the system. That's a very important reason. One, to keep it from freezing, but that's not the main reason. It's really the bacteria, and it's lubricating the design. Have you ever know it's kind of greasy when you ever feel it? Okay? So yeah, do they leak? Yes, they can. Do they most of the time? No, because of the coolant type that's used. So you don't want to go out and just grab an off-the-shelf coolant. Also, that coolant is designed for multiple metals. Transmitters today have aluminum, they have copper, they have stainless steel, they have plastic, and you think about all the different things that are involved. It's the same thing as an engine block. Most of the engine blocks today, cast iron block, aluminum head, they got plastics inside the thing, they got copper, they got brass, they got all these multiple metals. No different with the transmitter.
Okay. Stephen, thank you for your
Oh, you got
presentation. We got to go, folks, because we got another
If
presentation
you have
here.
a question, I'll be at the booth. Come by and talk to me. I'm happy
Yeah.
to help.
Hit Stephen at the Gates Air booth. We have another presentation here starting in just 2 minutes on modeling FM antennas.
Oh.